The International Space Station is a modular space station in low Earth orbit. It is a multinational collaborative project involving 5 participating space agencies: NASA, Roscosmos, JAXA, ESA, and CSA. The ownership and use of the space station is established by intergovernmental treaties and agreements. Want to know what's inside the space station? Watch till the end. Hey people, welcome back to our channel. In today's video, we'll be looking inside the International Space Station. The station acts as a microgravity and space environment research lab in which scientific research is done in astrobiology, astronomy, meteorology, physics, and various other fields. The ISS is used for testing the spacecraft systems and equipment needed for possible future long-duration missions to the Moon and Mars. The ISS program evolved from the Space Station Freedom, which is an American proposal which was made in 1984 to construct a permanently manned Earth-orbiting station, and the Russian Mir-2 proposal from 1976 with similar targets. The ISS is the 9th space station to be inhabited by humans after the Russian Salyut, Almaz, and Mir stations and the American Skylab. The station is basically divided into 2 sections. The Russian orbital segment is run by Russia, while the United States orbital segment is operated by the United States, as well as many other countries. Roscosmos has endorsed the continued operation of ROS through 2024, having previously proposed utilizing the elements of the segment to construct a new Russian space station called OPSEC. The first ISS component was launched in the year 1998, and the first long-term residents reached on the 2nd of November 2000 after being launched from the Baikonur Cosmodrome on the 31st of October 2000. The station has since been constantly occupied for 20 years and 353 days, the longest continuous human presence in low Earth orbit, having passed the previous record of 9 years and 357 days, which is held by the Mir space station. The ISS includes pressurized habitation modules, structural trusses, photovoltaic solar arrays, thermal radiators, docking ports, experimental bays, and robotic arms. The main ISS modules have been launched by the Russian Proton and Soyuz rockets and U.S. space shuttles. By August 2021, 244 astronauts, cosmonauts, and space tourists from 19 different countries have visited the space station, with many of them visiting multiple times. This includes 153 Americans, 50 Russians, 9 Japanese, 8 Canadians, 5 Italians, 3 Germans, and 1 Brazilian. The ISS has a huge number of external parts that do not require pressurization. The biggest of these is the integrated truss structure, to which the station's major solar arrays and thermal radiators are fixed. The ITS includes 10 separate segments forming a structure that is 108.5 meters long. The station was meant to have multiple smaller external components, such as 6 robotic arms, 3 external stowage platforms, and 4 express logistics carrier. While these platforms allow experiments to be deployed and conducted in the vacuum of space by providing electricity and processing experimental data locally, their primary function is to store spare orbital replacement units. ORUs are components that can be replaced when they fail or complete their designed life, including pumps, storage tanks, antennas, and battery units. Such components are replaced either by astronauts during EVA or by robotic arms. Multiple shuttle missions were sent to the delivery of ORUs, including STS-129, STS-133, and STS-134. The atmosphere on board the ISS is similar to that of Earth. Normal air pressure in the space station is 101.3 kPa, the same as at sea level on Earth. An Earth-like atmosphere provides benefits for crew comfort and is much better than a pure oxygen atmosphere because of the high risk of a fire, such as the one responsible for the deaths of the Apollo 1 crew. Earth-like atmospheric conditions have been kept on all Russian and Soviet spacecraft. The electron system on the Zvezda and a similar unit in Destiny generate oxygen aboard the station. The crew has a backup choice in the form of bottled oxygen and solid fuel oxygen generation canisters, a chemical oxygen generator system. Carbon dioxide is taken off from the air by the Vostok system in Zvezda. Other byproducts of human metabolisms, such as methane from the intestines and ammonia from sweat, are removed by activated charcoal filters. Double-sided solar arrays offer electrical power to the ISS. These bifacial cells take direct sunlight on one side and light reflected off from the Earth on the other, and are more efficient and operate at a lower temperature than single-sided cells commonly used on Earth. The station's systems and experiments use up a large amount of electrical power. Almost all of that is converted to heat energy. To keep the internal temperature in the workable limits, a passive thermal control system is built of external surface materials, insulations such as MLI and heat pipes. If the PTCS can't keep up with the heat load, an external active thermal control system maintains the temperature. The EATCS has an internal, non-toxic water coolant loop that cools and dehumidifies the atmosphere, which transfers collected heat into an external liquid ammonia loop. From the heat exchangers, ammonia is then passed into external radiators that emit heat as infrared radiation, then back to the station. The EATCS offers cooling for all the U.S. pressurized modules, including Kibo and Columbus, as well as the major power distribution electronics of the SO, S1, and P1 trusses. It can deny up to 70 kilowatts. This is way more than the 14 kilowatts of the early external active thermal control system through the early ammonia servicer, which was launched on STS-105 and installed on the P6 truss. The Russian orbital segment communicates with the ground through the Lyra antenna mounted to Zvezda. The Lyra antenna also can use the Luch data relay satellite system. This system fell into disrepair in the 1990s and so was not used during the early years of the ISS, although two new Luch satellites, Luch 5A and Luch 5B, were launched in 2011 and 2012 respectively to restore the operational ability of the system. Another Russian communications unit is the Voskhod-M, which allows internal telephone communications between Zvezda, Zara, Pierce, Poisk, and the USOS and provides a VHF radio link to ground control centers via antennas on Zvezda's exterior. The U.S. orbital segment makes use of two separate radio links mounted on the Z1 truss structure, the S-band and the Ku-band systems. These transmissions are directed via the United States Tracking and Data Relay Satellite System in geostationary orbit, allowing for almost continuous real-time communication with Christopher C. Kraft Jr. Mission Control Center in Houston. Data channels of the Candarum-2, European Columbus Laboratory, and Japanese Kibo modules were initially also routed via the S-band and Ku-band systems, with the European Data Relay System and a similar Japanese system intended to eventually complement the TDRSS in this role. UHF radio is utilized by astronauts and cosmonauts conducting EVAs and other spaceships that dock to or undock from the station. Automatic spacecraft are fitted with their own communications equipment. The ATV uses a laser attached to the spacecraft and the proximity communications equipment attached to Zvezda to accurately dock with the station. Let us know in the comments below if you found this video interesting, then be sure to hit the like button and stay tuned. See you again with another exciting video. Until then, goodbye.